thrust is needed to keep moving against space because it is frictionless. Here then, geocentrists want to invoke different kinds of space whenever it is convenient to do so. The obvious downside of the reality of space being essentially empty is that it has no viscosity and therefore no friction. It makes no difference whatsoever whether it is rotating around Earth, around Jupiter, moving in a straight line, doing a Highland jig, or sitting motionless. The idea that objects move with or against the flow of an arbitrary coordinate system is void. However, for the purposes of this video, we'll consider these two kinds of space rotating around Earth. The first job for any space program, of course, is to get into space. Otherwise, you haven't got a space program. How does this work in a geocentric universe? Everything in the sky supposedly rotates from east to west. With viscous space, it makes sense that the geocentrist rocket should not be launched against the flow, but rather with it. The geocentrist can use less fuel getting into space that way, and they can do this by either heading straight up, or preferably by heading west. With a static Earth and frictionless space, a geocentrist can launch rockets from anywhere and in any direction, with no difference in fuel consumption. The head-scratcher for geocentrists is why the world's space agencies launch expensive, heavy vehicles mostly to the east, from sites as close to the equator as possible. Do they really do this just to pretend that geocentrism is false? It's actually easier to launch to the east, and uses less fuel to achieve orbital speeds. We know an object must have a certain speed to move in a given orbit. Thus, the more speed you have to start with in the direction of your chosen orbit, the less you have to add by propulsion later. Since Earth rotates eastward, the closer your launch site is to the equator, the greater the speed boost you can get by launching in the same direction. Consider an observer watching a launch from a point above Earth as it rotates underneath him. A rocket sits on a launch pad at ESA's spaceport in French Guiana, 5.2 degrees north of the equator. It already has an eastward component to its velocity of over 1600 km per hour before it lifts off. This advantage can be carried through the atmosphere and out into orbit. If you launch to the west, you first have to undo the advantage that Earth's rotation provides, and then build up speed for a westward orbit. This means more fuel, heavier rockets, and a more expensive space program. Vehicles destined for polar orbits are launched westward in order to remove that eastward motion. Those destined for the inner solar system may also be accelerated in a westward direction to give them a transfer orbit that'll take them towards the inner planets. Space programs work the way they do and don't waste fuel due to a fundamental property of reality, namely geocentrism being bollocks. Assuming they got into space, can geocentrists explore the solar system with probes or manned spacecraft? With viscous space, rocket science for the geocentrist is easy. They can simply point a spacecraft at its destination and let it travel a straight line through rotating space. Of course, there is a slight problem with this idea. If space is in any way viscous so as to carry objects like planets along for the ride, a rocket heading out into the solar system has to move against the flow of space that is induced against it by its own speed. And of course, there's never just one problem. Geocentrist rocket scientists need to consider the crazier planetary spirals, in which the planets move up and down and round to produce the seasonal and distance variations that we observe from Earth. A geocentrist sending a probe to Mars must, like his heliocentrist counterpart, take account of where the planet will be in future. Here the similarity ends. Geocentrists have no mathematics to describe or predict the motion of anything, so they're a bit stuffed. Perhaps frictionless space can help. With frictionless space, there is a linear relationship between an object's distance from Earth and the speed it needs to move at to circle Earth once a day, notwithstanding variations due to craps, of course. How exactly do you put a craft in orbit around, say, Mars, when it would need to be barreling along at anywhere between 3,979 km per second and 7,446 km per second, depending on its distance to circle Earth once a day? There is only one force that can be exploited to put a craft in orbit around a planet. Sadly, it's not Mr. Space Hammerman this time either. It's that most familiar contender.
Gravity, you fucking retard!
Given the speeds of planets in their universe, the geocentrist rocket scientist has his margins for error reduced drastically. Arrives slightly ahead of time and his craft could simply be smashed by a speeding planet. Arrive at Mars just 10 seconds too late and the planet is nowhere near his craft anymore. Just a couple of seconds too late and you're still thousands of kilometers out and have zero hope of a correct orbital insertion. This is even more of a problem if we allow for the claim that gravity may mysteriously drop to zero at ranges short enough to explain geostationary satellites. Sticking with real gravity, if the craft arrived exactly where you expected it to in relation to the planet, it still stands no chance of getting into orbit around it. Although it didn't pass Mars itself, the fastest vehicle launched away from the Sun, the New Horizons probe headed for Pluto in 2018, passed Mars orbit at a speed of around 21 kilometers per second. With gravity assist, the Voyager craft were able to hit the 30s after their encounter with Saturn. The Mars Reconnaissance Orbiter was sent to the red planet with a fuel tank containing 1,187 kilograms of hydrazine. Over 70% of that fuel was used in one maneuver, a 27-minute-long rocket burn for orbital insertion. This put it into an elliptical orbit with a periapsis 400 kilometers above the surface and an apoapsis of 44,500 kilometers. MRO then spent 6 months using Mars